All right, so the first blank should be what? What is done? Good, work is done. And work is done. Good, when energy, which we'll talk about more starting Thursday, is used, and it applies a what? Force. And in order for work to be done, that force has to cause a what? Good, a displacement. Oh no, I ran out of space. And again, remember that the other thing that we talked about yesterday, when we talk about work, we're talking about the work of a specific force on a specific object. So the work of gravity on a falling apple. We could also talk about the work of air resistance on that same falling apple. Or we could talk about the net work being done on the apple in total. So kind of keep in mind the scenarios. Your options are to think about a specific force acting on the object, right, doing work, or all of the forces acting on the object, which is going to talk about net work. So that of net force over a distance. So it could be both. Make sure when you are reading a question, you're looking for kind of indicators of what exactly they're asking for. And when we talk about the specific force acting on the specific object, that's where examples like the carrying the tray around, how there's not any work being done on the tray. If we expand our understanding beyond the tray, there is work being done in that scenario, but it's between your feet and the floor, between your muscles and all of that. So there are cases where an object is moving, but no work is being done on that object because we're considering the system from a different perspective. So just make sure the formula is simple and all that, but make sure we are reading the setup carefully and understand like what point of view, what's the reference that we're looking at. All right, so into our actual notes for today. So today we're talking about power, and in this case, we are talking only about power as it relates to mechanical things. So we're not talking about electricity. That's a different discussion of power, and although it's related, we're not going to get into that. It's not actually covered on the AP1 exam, so it's not a topic that we get into. But power does go with electrical power as well, but that's not our current understanding. So power is the rate at which work is being done or the rate at which energy is used. So this ties into that pre-assessment question about who did, maybe it wasn't the door, I forget. There was a question about two students doing who did more work or less work, and they do the same work. What would be different is power. So when we talk about a rate of something, what should that indicate to us? When we talk about rates, we've used them before. Velocity is the rate of change of displacement. Acceleration is the rate of change of velocity. In both of those formulas, what are we dividing the variable by? Time. So power, which is measured in watts, like a light bulb, which is a little confusing because the symbol is W, and the symbol for work is also W. Power is equal to work divided by time. So how much work did you do? How fast did you do it? So a lot of times you'll see a question about how two students who have the same mass go to the top of a hill. Student 1 runs, student 2 walks. Who does more work?
They do the same.
Good. They do the same work, right? Same mass means same force. Same hill means same distance. Who generated more power while doing it? The one who went faster. So we want to make sure that we kind of keep those two things separate. That's the most common question because most people automatically jump to this idea of power versus work, right? You do the same amount of work getting to the top of the hill, no matter what. Power cares about how fast you go. So this is a good equation to look at the variety of equations that could be used in its place. So power itself is a simple equation. And on your formula sheet, let me see, it's written actually slightly differently. So on your formula sheet, and I've actually never noticed this until just now, it says that power is a change in energy over time. And we'll talk about that on next week. As far as how that is essentially the same thing as we're doing here. But if it takes energy to do work, when you use up energy, that change in, then work was done. And we'll talk about the mathematical connection to there. But that's how it's written on your formula sheet. So let's layer in, well, in my mind I think it was layering, but we're going to do some equation substitution. So power is equal to work over time. What can I replace work with? What's the formula for work? Good. Force times distance over time. So I've replaced that to here. What is something else that I could replace in this equation? Where do you see another variable's formula? Or something that you could replace with its own formula? What could we do there?
The parallel we can replace with cosine theta.
You could. We're going to leave that part out for now just to simplify. What is distance over time? Or displacement over time, rather? Good, velocity. So I can also substitute, and it is velocity because we would use displacement, so we'd have a direction. We can now say that power is equal to force times velocity. So we've substituted that in there. And what's one other thing that we could use? What could I replace force with? What's another way to solve for force? Good. So mass times acceleration times velocity. That one's sort of unlikely, but it's there. It could happen. So power is useful, even though it's an incredibly simple idea and a very simple formula, because it can be used a lot of different ways. So they can give you all kinds of different variables and ask you to get to power, which again is itself fairly basic, but we have multiple other options that look very different but mean the same thing. So as far as uses for power, a lot of times you'll see it as a proportional reasoning question. It's straightforward, it's easy, there's no squares or square roots or anything like that needed. So I'm just going to give you two quick examples. I want you to think about sort of what's proportional to what. So on the side, maybe make a list. So power is directly proportional remember, meaning if one goes up, the other goes up. What variables that if you increased would allow you to generate more power?
Mass, acceleration, velocity, force, anything but time.
Good, anything but time. So if you increase any of these things, also work, sorry. So if you increase force or displacement, you increase the work. It is only inverse to time. And I'm out of space. There we go. All right, so in a quick example, if a force does 4 times the work, in half the time, how much more power would it generate? Good, I heard 8 times more, right? So 4 times more work gets me 4 times the power, but doing it in half the time doubles that power, and 4 times 2 gives us 8. What if we did half the work in twice the time? Good, so we'd have 1/4 the power. You could see that as P over 4 in terms of how you might see it on a sheet, or it might say 4 times less. This could be 8P. All mean the same thing. And that's it for power. Fairly straightforward. If we were talking about electricity, you're doing work. Electricity is the flow of electrons. If the electrons don't move, then you're not using electricity. So it's about the force with which those electrons are being moved in a very sort of oversimplified sense. So while we won't be getting to that this year, that's the idea. All right, I'm going to give you a quick overview on just one option for how graphing could connect. So I'm going to give you one example. We'll kind of talk through it, work through it. I tried to keep the numbers really simple. But just to give you the idea of how you might see a graph. Remember, we talked to this idea that graphs can and will be used in a variety of ways, but we're looking at the same things on, sorry, I can go back, each graph. So what are the 3 features or parts of a graph that we might use for information?
Slope, position, data point under curve.
Good, so position would maybe be data point, but then area under the curve. So data point.
Are these notes too? Or?
Yes, I would add the.
I cannot see.
Sorry, this is just review, but I would add the example. So data point, area under curve, or the slope. All right, so any graph that I get or any graph that I need to make, one of those things should give me information that I can use. Whether it's the slope, and I've done linearization, so I've manipulated an equation to make or sort of force the slope to be helpful to me, or the area or anything like that. So an equation, or our equation, for example, oops. What is happening? Whatever. All right, so equations like our work equation, work equals force times distance times the cosine of theta, right? That assumes that the variables are constant. There's no room in this equation for variable amounts of force to be applied. It assumes a one constant force. So this equation assumes that force is constant. All right, just like in kinematics, we have to assume constant acceleration. But that's not usually what happens, right? If I'm trying to move something heavy, I probably didn't apply equal forces the entire time. At some point I needed more force, at some point I got tired and I used less force. So when something is non-constant, that's going to force us to use a graph. So non-constant variables lead to graphs. Right, that's why we use them. It shows how velocity changed over time. Velocity was not constant. It shows how your position moved over time. So there might be periods of where that variable is constant, but it actually allows you to see what happens when it changes. So we're going to use a position versus force graph, since we're working on this formula here. So position T versus force F. And the setup for this one is such that a force is applied to an object resulting in the displacement shown. So it's not a story or anything like that. You just have a basic distance in meters. Sometimes you'll see it as X for displacement again. Force in newtons. So this is 5, 10, 5, 10. So there's our line. So how could I use this graph to find work? What part of the graph? Data point, area, or slope? Good, area. All right, area is base times height. In this case, that would be force times displacement, which is work. So how much work did this object do during the course of its motion? All right, so we have two areas, right? We have this area here. Which would be your 7.5 times 7.5, which is, I don't remember the individual math. And then we have a triangle. Which would be 1/2 2.5 times 7.5. And later on with your calculator, if you feel so inclined, you should get 66.125. And then what unit do we use for work? Joules. The other question, or another question that I could ask using this same graph, might be about the time that the force was constant. Because if I have a constant force, what should I expect on the graph? What area is the force constant? How do you know? Red or blue? Red, right? The slope doesn't change, which means that force doesn't change. So here you have constant force. And here you have non-constant. So if I asked you how much power was generated by the constant force, how would you figure that out? What would be a little bit different than how we solve for work overall? What would you need to know? Good. So if the constant force was applied for 5 seconds, Eee. One minute. We're here till 8:01. Oh, that clock doesn't work. That one says it's 5 o'clock.
We have to do more hours.
Really long time. You got here really early.
I just looked at the long.
All right, so on this one, I still need to find work, but I only need to find work where? From what
The
point?
graph.
Well, I would find it from the graph.
Next question, what's that sign in the middle between the two, like?
Oh, it should be a plus, but it was a lazy plus. So we would find work just for this section. So you could do this all at once. 7.5 times 7.5 divided by 5. which is 11.25, and power is measured in what? Watts. So again, the question simply, one, it asks you to consider like where is constant? What does it look like on the graph to use a particular point of the graph? You're still solving for work, so you're still using area, and they're adding in power. We could calculate the power of the whole thing as well, as long as you were given time.